Great. Hello, everyone. It's great to be here. It's a very exciting time to be in the LLM space. So this talk, I'll be speaking about exploring what's like the absolute limit, uh, the extreme limit of what is possible today with LLMs in production, as well as the limitations that are currently hindering them and how you can address some of these limitations. Um, so let me, yes. Yeah. So quickly, just about me, I'm the CTO and co-founder of a startup based in Toronto called Bedrock AI, where I've been working on language models for the last few years. I'm currently writing a book on large language models, and I'm going to launch a GitHub pretty soon with content related to that book. The first two chapters, in fact, are about the ingredients that go into a large language model pre-training. While pre-training large language models is out of scope for most of us who don't have the compute, we can still do a lot of exploration just by looking at the data pre-processing pipeline, the tokenization, and various things. So yeah, I think when the GitHub is up, I'll post it to the Aggregate Intellect GitHub page. Um, so the what we are going to speak about today. So I want to talk a little bit about LLM evaluation. So when we are talking about hitting the limits of what is possible or looking at the limitations, you also need a very um, robust way of evaluating LLMs. But as we'll see, it's really hard to do that, especially when you have like the strongest performing model like GPT-4. It's sitting behind an API. You don't know when exactly it is being updated. You don't know uh, what goes into that model and what yeah, training set it is consists of, and so on. So it makes evaluation hard, but we'll see what we can do. And then I'll talk about you know some canonical tasks that I'm working on at my company that would probably stretch the limits of what is possible today, and we'll see why the limitations exist. And then I'll talk about some of the limitations that you get with the current paradigm. So there's like tons of startups that you can see today that use a combination of LangChain slash Llama index and then a vector database and then GPT-4, and then that's the startup. And they're like, this is replicated for all kinds of tasks and domains, but often you see that retrieval is the limiting factor, and we'll see why and how we can address that. And then there's also the context length limitation. Even at some point we were satisfied with 512 tokens context in the era of BERT, and now we are putting too much into our context. We are putting too much focus, even so that 32,000 tokens doesn't seem like it is big enough. This reminds me, the way that we are using context is so, I guess, inefficient. It reminds me of the old movie Memento. If anyone remembers, where that person in the movie had short-term memory, and every 30 minutes or so he had to like uh, start from scratch. And we are behaving in the same way right now. The other problem, limitation with calibration, which I'll go through, and also with factuality. I don't like to call it hallucinations. And then finally, I'll talk about the new trends after GPT-4, what LLMs we can expect in the near future, and so on. So as Amir said, like I have several hours of content. The reason is because I have this bad habit where I don't know if it's a bad one, but I usually prepare a lot more slides than I can cover. So every talk I give, I am able to cover like only 40% of the content. But if you feel any of these sections are like things that you want to be covered within the hour, then maybe you can put it in the in the chat, and then I'll skip some sections to cover them. So talking about LLM evaluation, um, so if you look at building useful products that are not just prototypes. So at my company, we have been having LLMs in production ever since we launched, and it's very, very hard because we are a fintech company which has a lot of the threshold for trustworthiness is really, really high. Getting something wrong can mean like $1 million loss in money or in reputation. So it's very hard to directly use LLMs. So the way that we have put things into production is to leverage the strengths of LLMs, but while limiting interactions with the LLM where they hit the limitations. So for example, we never ask financial questions directly to the LLM because LLMs are jack in the sorry, not jack in the box, jack of all trades. So they are meant to be generalists. So this is like, I guess, a rule of thumb. If you have domain specific data, and especially highly specific data, your custom models can always be better than any large language model that you have. And that holds true for us. So we have our own custom models, and we feed the financial questions to the custom models, and then we leverage the strengths of GPT-4 by getting the output of our models and feeding it into it, asking it to summarize or paraphrase it, so we get answers in a more structured form. So that's how we leverage GPT. So if you look at, I think there is no, this is probably well understood by everyone as of now. Like they are pretty good at code generation or for summarization, for instruction following, especially the recent models after you have instruction tuning and reinforcement learning, because the original GPT was like a petulant teenager, and it was very hard to get it to actually follow the instructions that you are using. And of course, query understanding. So the word understanding is loaded. It has very specific meanings in the context of linguistics and cognitive science. And there is like a long-standing debate about whether LLMs understand. For me, it doesn't matter. I'm using it as a in a layperson context. It knows what the query is. It may not get you the right answer, but at the very least, in most cases, you don't see it misunderstanding the query. But here, this is the main, I guess, thing that maybe people don't agree on, because reasoning covers a whole lot of things. So there are arithmetic reasoning, logical reasoning, and so many different types of reasoning tasks that exist, and you don't know, what are like the requirements for you to be, someone to say that you are good at reasoning. So I have this kind of test bench that I've been creating at home, that with a few reasoning tasks, and I've been trying it with all the LLMs that I've been able to test on for a few months now. So I'll talk about one of them, but before that, let me talk about evaluation. So one way to evaluate is to compare it with other models that have come in the past, especially the smaller models, especially if you have something already in production with a smaller model and you want to compare whether LLMs are actually good at it. So there was this really interesting thing called as the inverse scaling price, which I'll come to in a minute. But here are some things where we know that LLMs are, get worse, or language models get worse as they get bigger. They have higher capacity for memorization, which which may be a bad thing. And then there's the concept of bias amplification. So bias amplification basically means, like, if your pre-training data set is biased in a particular way. So for example, it associates in the term co-occurrences, maybe one religion is more associated with negative terms. And if it is if it is biased, let's say in a proportion of 10% more negative, in the actual behavior of the language model, it's biased by a lot more than 10%. So the larger language models are known to amplify bias. The other thing about language models, the larger language models, is that they also get overconfident, and we'll see later in the calibration section what that means. So if you, so I can show you here. So there's the inverse scaling prize was held mid last year. So this was held October 27. So this was 1 month before ChatGPT. And there are like really, really interesting cases where models actually get worse as they get bigger. So you can go through this, and I'll put it in the, in the GitHub later. But one thing to note is that 1 month later, when ChatGPT came out, and then after GPT-4 came out in March, most of this is outdated. So we already know this result. Inverse scaling can become U-shaped. So what does that mean? It means that, so you observe an inverse scaling effect. That means that when your model size becomes larger, your capacity becomes larger, however you measure it, for certain tasks, your performance becomes worse. But then if you continue making your model larger, it actually gets better in the end. And that's what you notice with GPT-4 being so, and Palm. So in this paper, I think they look at Palm, which is 540 billion parameters, and every single task here, I think not every single, but maybe most, where simply they showed this U-scale effect, where when the model became too large, it was again able to solve all these problems really well. So if so, just a quick like what exactly some of these problems are. One is an interesting one is this. So please answer the following simple algebra questions, and it asks a bunch, and then it asks what's the value of C, where the answer is slightly different, and then it asks another question, and then it was seen that the model would rely a lot more on the most recent few shot example than other few shot examples. If you put it like so, it's called the repetitive algebra task. Yeah. So going and then here is one reasoning fail that is part of the data set. Sorry, the task suite that I have been working on. And so this is a very interesting failure case. So you have the orientation of a city, streets. In this case, this is the city of Toronto. And here what I do is, so this is like the streets of Toronto, it's just set in a grid pattern. So it's north to south, west to east. And these are like the streets. So this is not the actual orientation. The actual orientation is College, Dundas, Queen, and King. But I shuffle the orientations so that, it doesn't pick from memory. The same here. And then I ask it, how do I go from point A to point B? Give me the directions. So you can try this using directly asking the question. You can use chain of thought prompting. You can use all kinds of, various prompting methods. But you can see that, so this is GPT 3.5 and this is GPT 4. And you see that, like I've been noticing the performance of this on various models and various tasks for several months now. And I see like there is a slow progress, but it hasn't been solved. So earlier, I used to see that, especially, the very first version of GPT 3.5, it would just go around in circles. It would say go left, go right, go left, go right, and it would just get lost. But now you can see that it gives you so. And then I was also seeing in some models, I was seeing that it was actually giving me the right directions as per the actual orientation of the Toronto city seats. Because remember, I have shuffled this. So it was actually fetching it from memory. Because if you go to the Wikipedia pages, it actually explicitly states like the directions. This is north of King and south of Queen and so on. So it was disregarding my instructions and it was actually retrieving the from memory. But here you can see it's getting better. And right now, I think the only problem in this one is that instead of turning right, it should have actually turned left to south and it would have gotten this right. So if you try this for like 100 examples, you can see that now it's kind of passing like 15% of the time or something. But so you can see that there's like a lot of reasoning fails. And this was a very interesting phenomenon that was reported last year, and you can see still see it. So there is this tool called Snoopy, and Snoopy. This is based on this paper that came out last year, and it's called Impact of Pre-training Term Frequencies on Few-Shot Reasoning. So what this means is the higher the term frequency of particular terms in your input, the better it is at solving the problem. And you can see it here, this interesting phenomenon. So this was GPT-J6B, and you can see when you ask it what is 24 times 18, it gets it correct. When you ask what is 23 times 18, it gets it wrong. And then you can see that the frequency of the token 24 is much higher than the frequency of the term 23. And then you can see any arithmetic operations which involve the number 23 are actually less performing. So this tool it allows you, so for example, I can put 89 and you can see that 89 is here. So this is accuracy versus in the pre-training set. So as you can see, like the bigger numbers will be like also having lesser frequency in the training set, but they will also have lesser performance. So this is it's not just for numbers, so you can test it for a whole lot of tasks here, and you can see what the effect of the pre-training frequency is. And often this goes back to test set contamination. And so one way to find test set contamination, so you can use tools like this, but there are other tools like Koala. So you can you can upload a file, or you can so you have something that is generated by a language model, and then you can say you can paste it here, and you can see if there was any overlap in the text. The other thing you can do is also, so this is C4, which is the data set that was used to pre-train the T5 family of models. C4 stands for the common crawl. It's colossal cleaned common crawl corpus, and basically you can also see what was already in the pre-training set. So these are like certain tools that you can use while you are evaluating things. And you can see, like especially with reasoning, you can see that there is a lot of evaluation, test set contamination that is amplifying your reasoning metrics. So let me, it's already 20 minutes. So let me quickly stop for in a second. And great analogy, but I guess so you're saying language models are good at linguistics and not other things. So from the point that I made, I guess it is, you can see that there are reasoning failures, and you can see that it's not well known how language models reason. You can see the impact of pre-training frequencies on reasoning, which can show that there may be some test set contamination that is not detectable. It's not that easy to detect test set contamination. So for GPT-3, the way they removed test set contamination was to do n-gram, I think it was 13 gram overlap. If there is a 13-gram overlap with benchmark sets, you remove it and so on. But it's not that simple. There's already a lot of test set contamination. And yeah.
Can I jump in quickly, because that was a slightly cynical question, and it's a little philosophical too. And I'm curious to hear your thoughts about this. So I do see a lot of people are talking about, like, proudly post on social media that, oh, I broke ChatGPT, it can't do math, or I tried to get it to do this financial thing and it can't do it, etc., etc. And some of the examples that you gave are also like that, like essentially getting directions and things like that. There are tools that are much better at doing those things. So why are we chasing this idea that language models should be one solution for everything rather than an interface?
Yeah.
At those things.
Yeah. So that's a really interesting question. So there is the consolidation effect that has been happening for quite a long time now, because earlier we were expecting models, we were constructing a model and we had a separate pipeline for each task. And then it slowly became, we are using the same model, but we are, fine tuning it multiple times every time for a different task. And now the consolidation is you use one model where, you can use, have a generalist model that can solve more tasks. But yeah, I think in future, the consolidation effect, there's certain driving forces that are leading towards that consolidation effect, and there'll be more and more work in that area, more and more consolidation happening. But as of now, and that's what I mentioned in my next section, is you don't necessarily need to rely on a language model for those things. And also it is like smart product design to not rely on language models for things that they are currently not good at, and exploring especially reasoning limits. So I haven't really seen very successful production level use cases where it explicitly relies on a language model's reasoning skills. So higher order reasoning skills, like the ones that we talked about here in the benchmark sets. Yeah. And then let me see. Is there a way to use prompt engineer to limit the context? In your prompt, you only ask the GPT. Yes. So yes. So it really depends on whether it has been, instruction fine-tuned in a particular way. But I noticed for plan T5, for example, if I am using a passage QA task, and then I use the prompt, answer. So I ask a question and then I say answer only from the information available in the passage. And then it's really good at following that instruction and not fetching something from memory. It's even though it has something. So you can see it, like, for example, I was trying with the financial question answers. I was experimenting with it, and you see, like the Flan T5, it is trained on C4, which has seen financial websites like motleyfool.com. So it knows who the CEO of Uber is, for example. And if I have a passage where I talk about, it contains the title, the CEO of Uber said, and something, but it doesn't explicitly name him. I don't want the language model to take it from its memory and say, and name the person. I can use that prompt passage. So that kind of prompting tech, I guess it differs because I didn't notice the same effect in some other models. I haven't. So I actually tried with GPT-4, and I think I've seen some instances where it was, picking from memory, even though I explicitly mentioned not to. And I think prompt strategies are never really robust, and I would not put, too much faith in them. Like it's not really the most productive avenue. I would say you would max out on your prompt optimization very soon.
Can we ask you something there?
Yeah.
What's the alternative if we can't rely on prompts to control the behavior? Although at the same time, in the previous answer, you also said that we are going towards consolidation.
Yeah. So we will go to eventually towards consolidation, but until then, if we are to put some things into production, we have to, rely on other means. And so I'm actually, that is topic number 3 and topic number 4, which I'll get to right now. So let me then go to, I guess I'll skim through topic 2 and topic 3 very quickly, and we'll go to the limitations right away. So for me, when I'm working on this at my company, I want to ask, I want the LLM to answer a question like this. Of course, yeah, so this involves a lot of task decomposition. So that means, who was the CEO of Apple when its share price was its lowest in the last 10 years? It needs to decompose in a variety of ways. A lot of subcomponents. So first, it needs to find today's date minus 10 years ago. And then it needs to find the share price. And then again, share price for the last 10 years may not be found on the internet. Maybe it needs access to a search API. So it needs a way to figure out what is today's date. So that means you need some kind of an external service to provide the language model today's date. You need a financial API to connect to the model that provides you with the share prices. And then you need to find, out of a list of share prices, you need to calculate the min function. So you need to find the minimum. And then you need to find who was the CEO of Apple on that particular date. But on the internet, there is no such thing where it is written, hey, on this particular date, this person was the CEO of Apple. So instead, you need to search who are the CEOs of Apple and what were their tenures. And then you need to figure out this date matches to which range in that tenure. So you can see that there are so many different subcomponents to this problem. And you need so many external tools that the LLM needs to leverage to get to this. So right now, this is not in production, but I think it is possible. I think this is something in the realm of possibility. So when we go through the next sections, we'll keep this in mind. Like this is the kind of complexity that we should be able to handle. So the other use cases, find me flight from Toronto to Bangalore, flying out of June 27, returning on August 12 without transiting via the US and without involving a self-transfer. So if you look at current airline booking sites, the limitation is, the UX or basically the UI widgets. So there is only a finite set of UI widgets that I can, filter through. But everyone has very nuanced things. So this is a real world use case for me. I'm not a Canadian citizen. which means that I can't transit via the US. So, but there is no, most airlines don't allow me, there's no button that says remove all transit from, remove all choices where the transit is via US. And I also, don't want to self-transfer, which means I want my entire baggage to be checked all the way to my final destination. And again, some websites might give you this, but I think whether you need a self-transfer or not is dictated by your visa requirements, which the websites themselves, the plane booking websites themselves don't handle. But you can imagine a language model doing this, especially a Expedia, like there's already an Expedia ChatGPT plugin, and I was able to use that to at least get this. So it can filter out things from US and so on. So yeah, so what are the tool integration paradigms? So one, it could be you ask a user query, and then you find the context that you need to feed to the LLM, and you do it using your LangChain, Llama index, etc. You may have to call, maybe it is text to SQL, get data from a SQL, and then you provide it to the LLM and synthesize an answer. Or this is the ideal case where you have a user query, and then the LLM decomposes the query into a set of tasks, and then it calls appropriate external services where needed. So that means we don't need to say, hey, you need to call this at this particular juncture. It knows exactly when to call the calculator, or when to call the financial API, or when to call the search engine, and where needed. So it also knows when to use its own memory. And then finally, when everything is done, it combines the response in a coherent answer in a requested format. So we'll go through each one of them one by one and see what are like the limitations. So let's start with the limitations of retrieval. And I'll just stop to see if there are any. Yeah, so DSP is promising, but it's really hard to implement in Promise. And of course, React, which is supported, I guess, by LangChain and so on. So, okay, so when we look at the limitations of retrieval, and I think, yeah.
Suhas, can I ask something about your Holy Grail?
Yeah.
The description that you wrote is something that I talked about in the previous talk, and there are some projects that we've seen that are trying to do this.
Yeah.
So before going to limitations, I'm curious to hear sort of a summary of what you think those projects are doing, and then we get into their limitations. So things like AutoGPT, Baby AGI, Hugging GPT, Microsoft Jarvis, and such.
Yeah. So, so what they try to do is to package everything into a single kind of tool, so that you will do this user query, and it does the rest. And you can see it even with the browser plugins for ChatGPT 2, and the way it uses, so it uses a few frameworks. So one of them could be the React framework, which you mentioned. But so for decomposition, you need a few strategies. How do you decompose when you don't know what? So when you are just given a task, and now you need to the user doesn't tell that your task needs to be broken down into X components. Like for example here, it doesn't do that. So how are you bound to do? So there are like a variety of different methods. The easiest method is basically you have a set of tools, and each tool comes with a description of what it can do, and then you basically match the description of that tool, the textual description, with an aspect of your initial user query and so on. So and then it calls a particular, so it uses chaining and it calls a particular service. So for example, maybe here it calls an API to get the share prices. And again, for that, you need to have like these things set up. Like for example, if you are calling an internal database, you need to have like the schema made available to it so that it can put the schema in the prompt so that it can generate a SQL query that can be called to a particular database, or an API call that it can construct. So you provide it like the API documentation and so on. So yeah, so the AutoGPT, Baby AGI, etc. They are all, I wouldn't say they are promising. I would say that they are projects that are, trying to work on this. They are definitely not, production ready for a very large number of use cases. But yeah, so I think we'll see in the coming days, like there will be like more methods and so on. So yeah, so talking about retrieval, I think one major case that we have seen. So there are like retrieval augmented LLMs. There's a long history of them. There are many models that use very complex retrieval strategies, etc. In production, what you are seeing these days, there's a vector store, there's a database of vectors. The vectors are encoding chunks of your data, and when a user query comes in, you match your user query with the chunk, and then you try to find the relevant context to answer that query. You feed that context into the model, and the model like GPT-4, and the model gives you the answer. But here, everything you are now limited by how good your retrieval is, and then especially if you are doing just cosine similarity, which is like very fast. That's the fastest way to achieve this, especially if you are working over a very, very large data space. So what exactly is cosine similarity? Yeah.
Do you mind going full screen? It's hard to read the text.
Oh, okay. Yeah. So what exactly is cosine similarity? So you have this embedding space, and cosine similarity is like you're measuring like a geometrically, the distance between two vectors in the embedding space. But how is that embedding space constructed? And then you have certain things to care about. So let me show you. So this is a very, very interesting paper. Problems with cosine as a measure of embedding similarity for high frequency words. So basically what this means is that cosine similarity underestimates the similarity of frequent words with other instances of the same word or other words across context. And this is because of the geometrical properties of the embedding space, where like low frequency words are more tightly clustered, and so there's like this whole explanation that goes behind it. And this shows that the cosine similarity, just using that metric alone, is already limiting you. But then the more important question here is what exactly, so you're trying to find similar documents, right? But what exactly does similarity mean? Because I think similarity is a very understated problem. It's very similar to sentiment analysis. And because sentiment analysis is one of those tasks which can, it's very underspecified. What exactly does sentiment analysis mean? Because it can be sentiment analysis changes with respect to who the person is. So this is a very interesting paper that I think everyone should read. It's from 10 years ago, but it shows you about the nuance that you have in these NLP tasks. So for example, here you can see this sentence: Lloyd Hessian, Chief Security Officer at BT Radiance in New York, said that virtualization also opens up a sleeve of potential network access control issues. So this sentence, it can be, it can be neutral sentiment, it can be positive, it can be negative. So this is like stating a fact, but it also might be a negative fact about virtualization. So if someone is looking at it from the perspective of virtualization, they'll see that this is maybe expressing a negative sentiment. However, if you are working in a security, in the security space, this is a positive sentiment because it's saying it's opening up a new opportunities for you. So you can see the same sentence, it can have so many different facets. Similarly, for content, the same content can have similar many facets. And I'll give you like an example, like imagine a sentence or a chunk of text that is talking about X person is been fired from company Y. And I'm going to make an embedding about it. And I want to say, I want sentences that are similar to this. But similar with respect to what? Is it similar? Do you want sentences that are talking about resignations? Do you want to match with text that is talking about that person X? Or are you looking at, things that are talking about the person Y? I mean, this is like a very kind of simple example, but you can see that when you take larger and larger chunks, this becomes really hard to imagine. And this is like, there is some initial work. So if I mean, this is not really a solution to that, but so there are instruction fine-tuned text embeddings. So where you can have, you can provide an instruction so that you can create an embedding catered to solving a particular task. So for example, is there an example here? So maybe you can't see this, but so you ask the instructor, so there is an input, and maybe you want to use that input for a particular task. You give it to the instructor, hey, I want this particular task to be solved for this input. And then it comes up with an embedding that is more, it takes apart that aspect of that input that is useful for solving this task. But basically, you can also have like faceted embeddings, which is not basically where you can have embeddings that are easy to generate that are focusing on particular facets of it. And yeah, so talking about Amir, what you were saying about the context lens, and basically using external tools. Yeah.
Can I actually ask a question on the cosine?
Yes.
Yeah. So on the cosine similarity, before we go forward, that came up in one of the previous talks as well. And the way I answered it there in the chat was that, in the context of information retrieval, normally when we can't rely on the query, we expand it, right? Like we expand the query so that it increases the likelihood of catching the right, overlap. And to me, chain of thought is essentially doing the same thing, right? Like one thing that is said might not have the right cosine similarity that we are interested in, but the fact that we get it to do a step-by-step reasoning, I mean code-on-code reasoning, I don't care if it is reasoning or not, but it is expanding really the query that is provided to it to increase the likelihood of getting the right cosine similarity. So, and I understand that might be for specific use cases, but is that how you think about it as well?
Yes, I think that takes you forward, definitely. So query expansion is helpful, and also chain of thought prompting, getting rephrasing the queries in multiple ways is also helpful. But the fundamental limitations still remain, I guess, because the other thing that you want to like when you are building production level applications, of course you can chain them and so on, but you are again limited by a context length, and it is much easier and it's also much more robust and reliable if you have somehow gotten all the context that you need. So it's this is like a precision versus recall thing. Let's say I want, in order to answer this particular question, and it is strewn across multiple documents, multiple chunks and everything. I want everything to fit it in the context window when I'm doing the answering in a single context window, rather than having to chain it across multiple times, because the context window is too large to hold all the context that is relevant to this particular, to answering this particular problem. So when that happens, yeah, so again you hit that like retrieval. Again, it depends on how complex your user queries are and how. So I think whether something is production ready or not here depends vastly on the complexity of user queries versus the complexity, or not the complexity, but I guess the dense density. I'm not sure of the proper word, but imagine your information that you need, how distributed it is across your corpus, across the data set on which you have your vector database. In some cases, for example, you may have to only visit one document. All the things that you want is present in one chunk or in one document. But in different types of queries, it is distributed across like the entire document, and not the entire document, entire corpus across various documents. And you'll have to coming up with the right context for that becomes much more harder. Yeah, so again, the context length. And when we see the context length, and I noticed this for one of the tasks that I was working on, it was a fairly complex task. And then I started putting in more and more and more instructions until the instructions became so long that, you know, it was like 1,000 tokens with just, not 1,000, I think it was, yeah, more than 1,000 tokens of just instructions. And this is like, so now every time you call the language model for this particular task, you have to prefix this gigantic instruction. And I think this is also one of those driving forces that are pulling people away from in context towards fine tuning, because as your context becomes longer and you have to feed the context every time. So we'll talk a little bit about caching and everything a little further along, but you want to save money. You don't want to have such a large degree of context being fed to the model every time. And then you see, hey, wait, this is probably best done by fine tuning. And then suddenly fine tuning starts becoming more helpful. So one thing, so these are like from my personal experience. Fine-tuned models for very specific problems always work way better, even against GPT-4, especially if you have domain adapted and task adapted continued pre-training. So this is basically you are taking a model, let's say a 20 billion parameter model like GPT-NeoX, or even a much smaller model like GPT-J, 6 billion. You do continued pre-training on your domain data and on the kind of data that you see in your tasks. And that helps a lot. And then fine tuning, yeah, on a specific model. So again, there is the consolidation effect happening, but for if you want to solve particular well-defined use cases, fine tuning is still works really well, and it's also more and more sample efficient. So you have so many new techniques, set fit, and a lot of other parameter efficient fine tuning techniques also. So where you don't have to fine tune like the entire model. You have adapters, LoRa and adaptation. So basically, so you only tune a very small set of parameters. So I think that's going to be like become more and more prominent over time, and more importantly, in-house instruction tuning. So this is basically Alpaca, but on your own data set. And I just saw an announcement by a company like just 5 minutes before the talk started, where I think there's a company that is promising, like it hasn't been launched yet, but they're promising that you can do something like Alpaca, but for your own domain in in a few lines of code and something like that. So yeah, so these are some arguments for fine tuning, but you have things like for in context, you have things that so there is something called as prompt gist that came out like very recently, I think maybe a week ago, which I think is very, very promising. So the way prompt gists work is, so for example, this is the prompt. So you have T, which is the instruction, X is the input, and Y is the output. So in this case, the instruction is translate this to print, and this is your prompt tokens, and this is your input tokens that are part of the prompt. The input is basically what you want, in this case, the cat, and then you have the output tokens. So this is the normal prompting strategy. You can do fine tuning, where fine tuning means this whole thing is encoded inside the model. So this distribution, T, this T comma X, instead it becomes like T is encoded in the model, so that now you have Y given X. It learns to find the output for each task, but you have to do that separately. You have like you fine tune it T3 for this task, T2 for this task, and then finally you don't need to give any prompt at all. But the prompt gist is like something in the happy middle where you do prompt compression. So during training, or actually during instruction tuning, what happens is you so you define something called as a gist token, and basically the gist tokens are supposed to contain a compressed version of the prompts. And not only are they supposed to contain a compressed version of the prompts that you have fed it during the instruction tuning phase, they are also supposed to generalize to prompt types that it has not seen before. And the way this works is so the normal autoregressive decoder, G1, G2, and you put some prompt gist tokens here. And then during training, you don't allow these tokens to be able to see this explicit instruction, but they attend only to the prompt tokens. So this forces the prompt tokens to encode whatever is here and however large it is into this compressed space. And so that's basically the idea. Anyway, I guess it's 2:55, so I'll quickly like go through what I was planning to talk, but and then
Suhas,
yeah.
We are actually out of time.
Oh, okay.
Yeah. we need to take a few minutes break before the next talk. But out of the material that you have left, maybe spend about a minute on the most important part, and then we'll go to a break.
Yeah. So one thing is the overconfidence or the calibration. So that means if you look at the confidence of BERT, so this is like the probability score, like probability of a particular token, even if it's like the wrong token, if it has a very high probability, is it more likely to be correct? So that is what we are asking when it comes to calibration. And you can see that BERT, Roberta, all the smaller ones are more calibrated. So that means when it gives a probability score that's like 0.67 or something, it's more likely to be wrong. But here with the larger models, if it is giving a probability of 0.9, it could be wrong, but it could also be, I mean, that same calibration doesn't hold. So